In this video, we're going to talk about the gradient of multivariable functions. If this video is helpful to you at all, please leave a like, and if you'd like to see a video on anything else, leave a comment letting me know. Now let's get into it. So if we have some function in three-dimensional space, right? Let's say that this function is f of x, y, right? Then what this function is it takes an x value and a y value as input. So down here, I'm going to say that this is our x value and this is our y value. And then the height that's outputted here, this is f of x, y, right? That's the result that we get from this function right here. All right, so now let's consider if you were a little guy, right? And here's your little man, right? And I take that guy and I drop him somewhere on this graph. Say I put him right there. Well, if we look at the xy coordinates for that, that's going to put us down here, right about here. Let's say that you're right there. Now, say that I want to know which direction I would have to travel to go up the steepest incline. So let's just look at this at where the person is. It looks like it kind of goes uphill in this direction. And if I traveled this way, that would be the steepest direction that I could travel, right? I would be going up the fastest that I could. The slope is going to be the maximum, right? Now, if I took a projection of that arrow and I went down this way, then that arrow looks like this, right? It just says, hey, travel in the x direction and you'll be going as steep as you could. What this arrow is the output of what we're going to talk about, which is our gradient function. So we have, if you were looking at this, we have our original function, and then we write our gradient function like this, sort of an upside down delta character, right? F of x, y. And this equation is characterized by, it spits out a vector. What does it spit out as a vector? It spits out this vector right here. You give it some point, and it gives you this vector down here for that point. Now, what does that mean? What that means is that if I took this guy and I moved him somewhere else, say I move him right here, then it's going to look down here and say, okay, well, at this point down here, which direction would I travel to go uphill the fastest? I would travel this way to go uphill the fastest, right? That's going to take me up this way, which would be the steepest incline. So what this function outputs is simply the direction in which, right, I would have to travel relative to the xy plane to go uphill the fastest. It's going to give me this vector. So the x component of this vector is going to be the partial derivative of f with respect to x for the x component of the vector, and then the partial derivative of f with respect to y for the y component of the vector. It may not make intuitively a whole lot of sense why this is, but just bear with it, and it's actually a very simple method to apply. So let's use this to solve some. Let's use this to solve some equations, or not to solve some equations, but to work some problems rather. The first problem that I want to work is, let's say that f of xy is equal to x squared plus y squared. And I want to know what the gradient is at, I don't know, let's say 3, 5. Cool. Well, first we need to make our gradient function. And we remember that gradient function of x, y is equal to, spits out a vector, the first component of which is the partial derivative of f with respect to x, right? Second component being partial derivative of f with respect to y. So we need to define both these partial derivatives. Partial derivative of f with respect to x is equal to 2x, right? Because y is just a constant. And then the partial derivative of f with respect to y is 2y. So then we take both of these and we plug them back into this equation here. And that's going to give us, what's that going to give us? That's going to give us that the gradient of f of xy is equal to the vector 2x, 2y. Awesome. Now that we have this equation, what do we do with it? Well, we were given a point that we wanted to find the gradient at, right? We were given this point right here. So find the gradient right here. So what are we going to do with that? We're just going to plug it right into here. Right into our gradient equation. And that's going to give us that the delta f of 3, 5, right, because that's our point, is equal to 2 times our x component, right, so 2 times 3, 2 times 3, and then 2 times our y component, so 2 times 5, which is just equal to 6, 10. Now what does that mean? That just means that the direction in which we would have to be facing to go up the steepest incline at 0.35 is a vector of 6 in the x direction and 10 in the y direction. All right, so let's do another one. This time, let's do another xy, f of xy. So f of x y equals e to the x plus y times sine of x minus y. All right, so we already know that we're going to have to find the partial derivative of f with respect to x and the partial derivative of f with respect to y. So we can find the derivative here pretty easily with respect to x. So e to the x plus y, because y is a constant, and e to the x plus a constant is the derivative of that is just e to the x plus a constant, multiplied by, since we took the derivative of this first part, then the second part just stays the same, sine of x minus y, plus This time we'll keep the first part the same and do the derivative of the second part. Well, the first part stays the same, so x plus y. Derivative of sine is cosine, and then x minus y, because derivative of cosine or of sine of x plus some constant is just cosine x plus some constant. Okay, now with respect to y, we do e to the x plus y, because that's the derivative of the first part, multiplied by sine x minus y. And then we're going to do plus e to the x plus y multiplied by, okay, well now we have to do the derivative of the second part with respect to y. And what that's going to come out to is cosine x minus y, but we have to take derivative of the inside, right, with respect to y, which in this case it's going to come out to negative 1. Before it came out to 1, so we just didn't bother writing it, but now it comes out to negative 1. Okay. And then that negative 1 can come over here and just make that negative. Great. And now we have our two different parts, and we could write our function as such. Equals, and I'm not going to rewrite the, actually, you know what, I will. I'll just take this, throw that in here, comma, and then and there you go. That would be your complete gradient function. And they could ask you for a point, and you would already know how to plug that in and figure it out. Let's try another one, except this time let's do 3 variables instead of 2. So f of x, y, z equals x squared. Let's say that it's x squared times y plus y squared times z plus z squared times x. Now for this one, we're not working with 2 variables anymore, we're working with 3, but the same idea applies. And that is that instead of just doing the partial derivative with respect to 2 of them, now we're doing the partial derivative with respect to all 3. So the gradient function of f of x, y, z is a vector that has 3 components, an x and a y and a z component. Partial derivative of f with respect to x, partial derivative of f with respect to y, and guess what comes next? Partial derivative of f with respect to z. Now we have a 3-dimensional vector, right? But if we were to think about how this graph looks, it's a 3-dimensional domain, but it's a 4-dimensional graph, and we're not even going to bother visualizing that. But the method for developing the gradient function stays exactly the same. So let's figure this out for the point, say, 3, 2, 1. Make it easy. All right, so let's solve for each of these partial derivatives. So partial derivative with respect to x would be 2xy plus z squared, right? Then we have partial derivative with respect to y would be 2y, let's see, 2yz plus x squared. Partial derivative of f with respect to z would be 2zx plus y squared. All right, now all that we have to do is evaluate each of these. So we take this guy right here and we plug it in here. And that's going to come out to, well, the first one is plugging 3 into the partial derivative of f with respect to x. So that's going to be this function right here. So it's going to be 2 times, well, what's our x value? 2 times 3 times our y value, which is 2, plus z squared, so 1 squared. Okay. Then our y value, we're going to do the same thing. So 2 times our y value, which is 2, times our z value, which is 1, plus our x value squared, which is 3 squared. And then for our z value is 2 times our z value, which is 1, times our x value, which is 3, plus our y value squared, which is 2 squared. And if we simplify all that out, we get 2 times 3 times 2 equals 4 times 3, which is 12, plus 1, which is 13. And then 2 times 2 times 1 is 4 plus 3 squared, which would be 4 plus 9, which is 13. And then we have 2 times 3 is 6, plus 4 squared is 10. And there's your gradient vector. So there's your answer. All right, let's do one more function of 3 variables, and then we'll call it. Let's do f of x, y, z equals ln, the natural log of x squared plus y squared plus z squared. And we're not going to bother evaluating at any point. I just want to know what the gradient function for f is. So gradient function of f of x, y, z is equal to the partial derivative of f with respect to x, partial, or gives us a vector with these components, partial derivative of f with respect to y, and partial derivative of f with respect to z. All right, so let's start figuring these out. So you got partial derivative of f with respect to x is equal to, well, we take the derivative of the whole thing and then multiply it by the derivative of what's inside. So the derivative of ln of anything is 1 over that thing, right? So you go 1 over x squared plus y squared plus z squared. We multiply it by, okay, what's the partial derivative of the inside with respect to x, right? And that's just going to come out to 2x. So this just is, well, we can take that 2x and we can go ahead and throw it on top. 2x. Great. Partial derivative of f with respect to y, we do the same thing. We have 1 over the inside, so x squared plus y squared plus z squared. And just like before, we have 2y as a partial derivative. We're going to go ahead and throw that 2y on the top. And you can already see a pattern here. For z, it's just going to be, well, it's going to be the same thing, right? X squared plus y squared plus z squared on the bottom, and then 1 times 2z on the top. All right, so now we have all of our different components, and we can go ahead and write out what the complete equation for the gradient is. And after copying everything over into the different slots that we have here, after substituting each of these in, uh, this is this is our answer. All right. Please let me know if there's anything else that you'd like me to go over. If this was helpful to you, please leave a comment and like, and have a good day.